Hello, my name is Quesada Torres. I work as engineering manager in the Site Reliability Engineering Department, or SRE department, at Google. We SREs often manage and support very large distributed services. Services require resources to run, for example, processing power, memory, storage, and network. When services are large, the large quantity of required resources are expensive and may need time to deploy. When using public or private cloud solutions, resource allocation may be as simple as increasing the resource demand in a config. When owning the hardware, resource allocation may involve buying and installing hardware. Proper management of resources keeps services running and keeps them running efficiently. In this tech talk, I am going to discuss some of the complexities of capacity management for distributed services. I will introduce common resource classes and some of their most notable particularities. Then we will see the difficulties in resource provisioning, that is, the process of appropriately allocating resources for each of the parts of a service and for the service as a whole. We will discuss load testing, a tool that helps measure how much load a service can serve and that enables engineers to size the service properly. I will go through the complexities of capacity planning, that is, the process of forecasting the resource demand of a service and securing the supply of resources for it. Finally, I will wrap up by presenting some good practices on the implementation of capacity management solutions. Before we start, I will define a few terms that I will use throughout the talk. I will use the term task to refer to an instance of a binary running on a computer. The term job will refer to a set of tasks, that is, a collection of instances of the same binary running on one or several computers with the same configuration for redundancy or scalability purposes. Assuming the work is at least somewhat parallelizable, we can add more tasks when we need to grow the capacity of a job. I will use the term service to refer to a system that provides some functionality for other systems. It could be a front-end, a back-end, a combination of a front-end and back-end, or something else entirely. A stack is the set of jobs that comprise a service. A service may consist of several stacks. The production stack is the stack that serves most of the production traffic. The canary stack is a stack that serves a small fraction of the production traffic. Rollouts or production changes are tested in a canary stack before they land on the production stack so that unexpected behaviors can't impact all production customers. I will use the term region to refer to physical locations. Synonyms of region could be data center, zone, or cluster, depending on the context. For example, in some cloud solutions, regions have several zones. I will stick to region to distinguish different physical locations. A replica is a copy of the service stack for redundancy, scalability, or latency purposes. For example, the production stack of a service can have replicas in 3 clusters or cloud regions across the world. Finally, I will use the term utilization to refer to the percentage of a resource that the service is actually using. For example, a storage utilization of 97% for a service means the service is using most of the storage available and could soon run out of space to store any new data. Let's get started with resource classes. The table in this slide will show a summary of common resource classes that services use. Depending on the infrastructure solution, some of the resources may be allocated directly at hardware level and some may be allocated behind some abstraction layer. For example, at hardware level, a certain amount of hard disk drives of a certain model could be allocated. At a higher level, storage could be allocated as space, bandwidth, and input-output operations per second. CPUs provide processing power, which is needed to run any operation. Not only business logic specific to the service, but also processing the inflow and outflow of requests in a task, routing requests to other tasks, managing and serving cache data, or maintenance tasks. If processing power is ever a bottleneck for tasks in the critical path of user-facing services, users will perceive increased latency. In the worst-case scenario, users would perceive ever-increasing latency because requests are piling up. If the situation persists, the queue of requests will grow even larger and requests will start timing out. This will continue until the incoming traffic drops and the service can catch up, or until the service is restarted. Processing power is hard to measure and plan for. Different CPU models offer a different processing power per unit of time, and their throughput actually depends on the concrete application that is running. Different programming languages, services, frameworks, libraries, operating systems, and technologies have a different CPU overhead. Memory management, garbage collection, and libraries cause different baselines of CPU usage. When there are more tasks running on the same machine, these tasks can interfere, for example, by putting more stress on their own CPU memory caches. Also, when running on a symmetric multithreading CPU, where one core will present itself as multiple slower cores. Only when a task is the only occupant of a physical core will it get the full processing power of that core. On top of that, it is impossible to monitor actual CPU usage because traffic patterns, the operating system scheduler, background processes, and the service software itself introduce noise on CPU usage. A materialization of this issue is that latency can significantly vary between requests that are identical. Memory, RAM, stores the operating system, the task binary and its libraries, data needed by the tasks running, and task state as it runs. If a task tries to use more memory than allocated, it will crash with an out-of-memory error or even cause the operating system to thrash. When memory utilization is high in languages with garbage collection, tasks start heap thrashing, that is, triggering garbage collection too often, almost continuously. Thrashing uses up any remaining processing power and significantly degrades the performance of the task. It often ends in an out-of-memory error. It is even harder to measure or plan for memory usage than CPU usage. Different programming languages, services, and frameworks have a different overhead on RAM. Some software may not manage memory properly, which causes memory leaks, that is, ever-increasing RAM usage that will eventually make the task crash and restart. It may be hard to monitor actual RAM usage in languages with garbage collection. RAM usage metrics will only be meaningful right after garbage collection happens. Even then, different services have different requirements on RAM. For example, caches use RAM to store and serve cached data and often run at high RAM utilization without risk of crashing. High RAM utilization is not necessarily a sign of issues. Different usage patterns of RAM can have a strong influence on the perceived speed. Locality of reference is the most important factor. When the software accesses RAM in a predictable pattern, then the CPU cache helps a lot. When the software accesses RAM in a random fashion, it will be a lot slower. Services often need to store data and read it, and they do so on hard disk drives or solid-state drives, either directly interacting with the hardware or by means of a storage service that abstracts storage drives. Storage can be described in terms of disk space, bandwidth, and input-output operations per second. Storage space is simple. Either in hard disk drives or solid-state drives, data needs to be physically stored in a storage medium. If the service runs out of space, that means writes will fail, and perhaps even reads will fail if reading somehow involves writing. For example, if the service or storage solution needs to store Paxos state to do consistent reads, or if the storage solution needs to keep track of what data has been accessed and when it has been accessed. Storage drives offer a specific read or write bandwidth that depends on the technology. Hard disk drives contain disks, platters, that are spinning. Read-write heads are placed in an arm held over the platter and read or write data as the platters spin. The bandwidth of a hard disk drive depends on the rotational speed of the platters and the data density. That is, how much less space is needed to store a bit. Fun fact, the inner tracks of a platter have a smaller surface than the outer tracks and therefore offer lower capacity and bandwidth, sometimes even 60% less than the outer tracks. Solid-state drives do not rely on spinning platters. They rely on flash memory or similar solid-state technologies without moving parts. So the bandwidth they offer is way higher than hard disk drives, and they have no such thing as inner tracks. The more drives the data is spread across, the higher the aggregate storage bandwidth is. RAID is a low abstraction level solution to scatter data across drives. Storage services are higher abstraction level solutions that manage up to thousands or millions of drives. If storage bandwidth is ever a bottleneck in a user-facing service, users will perceive increased latency. In the worst-case scenario, requests could pile up and eventually start timing out and cause an outage. The throughput perceived by the software accessing the storage drive is typically lower than the theoretical bandwidth because the data is rarely read sequentially from a storage drive. For example, multiple layers of indexing may need to be looked up to figure out where the desired data is actually stored, and also because the read-write heads need to be repositioned over different tracks to read data from them. This particularity is captured by a term called input-output operations per second, or IOPS. The input-output operations per second, or IOPS, a drive offers are inversely proportional to its seek time. In a hard disk drive, the seek time is the time it takes an actuator to move the arm that holds the read-write heads in an arc over the disk. from the inner to the outer tracks and vice versa to seek the track where the data is stored. Solid-state disks do not have actuators nor moving parts, so their seek is faster than hard disk drives. Therefore, solid-state disks also significantly outperform hard disk drives on input-output operations per second. The more drives the data is spread across, the higher the aggregate input-output operations per second are. So RAID and storage services that manage many hard disk drives are good approaches to increase the throughput of storage drives. If input-output operations per second are ever a bottleneck in a user-facing service, users will perceive increased latency, and if the situation is not resolved, same as with storage bandwidth, eventually an outage. The operating system or the software often runs some maintenance work on the storage, for example, building or rebuilding indexes or compacting data, that is, aggregating changes that were stored as incrementals. Maintenance work will decrease the perceived throughput of a disk compared to what the disk nominally offers. The storage space and bandwidth of hard disk drives increases over time as the technology progresses and disks can store data more densely. However, the input-output operations per second of hard disk drives doesn't increase because seeks are still needed and the disks cannot spin faster and faster. The spin rate is mainly 7.2K revolutions per minute, with some more expensive disks rotating at 15K revolutions per minute. This is about mechanics that can simply not go that much faster. Disk seek times have not improved a lot over the past 20 years. Because of this, the determining factor of how many hard disk drives are needed for a service may currently be bound on the amount of data that can be stored on a single hard drive, but as hard disk drives improve, the number of drives needed for the service could shift to being bound on the input-output operations per second of each drive, and as a result, leaving available space unused on each of these drives. Solid-state drives are currently more expensive than hard disk drives space-wise, but they have a way higher input-output operations per second and bandwidth. A good use of solid-state disks is using them to cache or directly store the data that the service reads and writes the most often. If your service is bound on input-output operations per second, it can be cheaper to use solid-state drives than to use many hard disk drives of which the storage capacity is not fully used. Network resources enable the communication between users and a service and between the service and its dependencies. Network resources include physical connections and bandwidth between racks inside of a data center, between data centers, or between faraway regions such as Europe and the United States. If the network is slow, it intuitively causes increased latency. If too many packets are sent, some will be dropped and need to be resent. If network bandwidth is insufficient and becomes a bottleneck, it will cause increased latency and ultimately an outage when the service cannot catch up with the requests and they start to time out. Cables and network infrastructure can also break, forcing traffic to take a longer physical path through the network or even leaving a whole region disconnected. Services can have dependencies on other services they use as backends. These backends can be critical dependencies if they are needed for the service to function at all, or soft dependencies if they provide some best effort feature and the service would be degraded but still functional. A backend failing to serve requests from a service timely may trigger an outage. A backend not being able to stand the throughput required by a service will cause increased latency and, depending on how critical it is, degraded serving or an outage. If you deploy a quota system, quotas can help limit the throughput between services and the backend in order to provide some isolation between services using that backend. Whenever a service sends more requests than expected and it hits the quota limit, it would be throttled by the backend instead of overloading it and hurting any other services using that backend. Services may also require other resource classes such as graphic cards or specialized hardware such as artificial intelligence accelerators or storage tape. Some examples of the effects of these resources being insufficient are slower machine learning training, slower backups, or inability at all to do backups. Let's now discuss resource provisioning. Services need the right allocation of resources to run properly. That means enough CPU and RAM overall, enough CPU and RAM per task, enough storage space, bandwidth, or input-output operations per second, enough instances of tasks across the jobs that constitute a service stack across regions, and others. Resource provisioning can take any kind of demand input that makes sense for the service, such as requests per second, total users, active users, items stored, size of corpus, any similar metric, or a combination of them. The output is the production layout with specific sizes and allocations. For some organizations, this means buying and installing hardware. For others, scaling up on some public or private cloud. In all cases, provisioning must be backed by some real hardware, but it is very useful to think of it in the abstract dimensions of the resource classes. Why is resource provisioning needed? Well, a task that is undersized and hits bottlenecks on CPU usage, crashes on not enough memory, or has other issues related to lack of resources causes increased latency or errors. Not enough instances of a task running would cause similar issues. A task that is oversized, running more tasks than needed, or allocating much more storage or network capacity to a service than needed, make the use of resources inefficient and hence more expensive than needed. Resource provisioning is critical because both reliability and resource efficiency are critical. The only exception are services with a negligible running cost. In that case, efficiency is likely less important. Throwing some extra padding of resources can guarantee the service reliability while keeping the effort on provisioning very low. Why is resource provisioning hard? Well, large services are complex, and many of their complexities show up when provisioning for resources. Services often use several resources, often in different regions and with several different priorities. The amount of data points associated with resource provisioning for a service can be large. If a service is evolving fast, it lives in a constant flux state where resource provisioning often needs rework at the risk of it becoming obsolete and causing outages or introducing inefficiencies. For example, feature launches, customer adoption, refactorizations, architecture changes, and changes in backends and libraries can entirely alter how a service uses resources. The production setup itself can be chaotic if other engineers or automation are making changes simultaneously. Services may be constantly undergoing a combination of rollouts, resizes, relocations of the service, deployment of changes, experiments, turn-ups, and turn-downs. The engineers working on resource provisioning can be in a constant state of trying to catch up with production, especially when there is no proper automation to deploy the changes safely and the engineers need to deploy them to production manually. That frustrating manual work, sometimes called toil, is a constant burden that slows down the implementation and improvement of the resource provisioning solution and automation. The target utilization is defined as the highest possible utilization that allows the service to function reliably. When provisioning a resource for a service, if the resource utilization is low, the service is inefficient because it has more resources allocated than it needs and resources aren't free. If resource utilization hits 100%, that resource becomes a bottleneck and the service suffers from increased latency, increased error rate, or even an outage. Let's focus on CPU, one of the easiest ones to explain because the higher the load is, the higher the resource usage will be. Let's assume that the number of requests the service receives drives the CPU usage. The relation between requests per second and CPU usage is non-linear for many reasons. For example, there is an overhead associated with the data structures the software and operating system use to manage requests when the load is high. So even when a service is not serving requests, it is using some CPU. For example, more queries may lead to more complex garbage collection also happening more often, or conversely, more queries may share more cacheable elements and therefore be cheaper per request. Assuming non-constant load, which is true for many services, intuitively, resource utilization should hit 100% of the allocated resources when the service is handling peak traffic. That means the service has sufficient resources allocated to it to serve the peak and is not over-provisioned in any wasteful way. Please note that at non-peak, utilization will be below 100%. This drives the average utilization down. Peaks depend on the source of request of the service, which is often a user base. For business-related services, early business hours drive the weekday peaks. For social-related services, peaks may happen late in the afternoon, at night, during weekends, or coinciding with social events such as concerts. When an unexpected event happens, usage can soar very quickly. If a service runs worldwide, the spread of the user base across different time zones forms a complex daily traffic pattern. Estimating the peak usage itself is not trivial. Depending on the granularity considered, the peak will look different. Let's review with an example. So one day, a fictional service handles the demand peak, 1.3 million requests per second, exactly at 8:32 a.m. If monitoring probes for the load once every second, it captures the peak of 1.3 million requests per second. If monitoring probes for the load once every 5 minutes, it could capture a lower peak, 1.2 million requests per second on average between 8:30 and 8:35 a.m. If monitoring probes for the load once every hour, it captures a peak of 1.1 million requests per second on average between 8 and 9 a.m. With different granularity, monitoring can perceive the peak at different time of the day. If the time window is 1 hour, traffic from 5 to 6 p.m. averages at 1.2 million requests per second. That is more than between 8 and 9 a.m., even though the demand peak of 1.3 million requests per second happens in this time window. With a 1-hour time window, monitoring would perceive the peak between 5 and 6 p.m., while with a 1-minute time window, monitoring would perceive the peak between 8:32 and 8:33 a.m. The requirements of the service drive the requirements of the resource allocation. For a non-real-time service that has a latency service level objective of 10 minutes per request, provisioning for the load as measured with a 5-minute time window is okay. Now picture a user-facing service with very strict requirements on latency. Let's say requests time out after 100 milliseconds. Provisioning for this service requires fine-grained data. Provisioning for the peak with, say, a 1-minute time window wouldn't be enough, as a burst of traffic that is a few seconds long could be completely missed, causing unforeseen resource exhaustion and request timeouts. If a service runs on several tasks, proper load balancing should take care of spreading the load across the different tasks so that utilization is well balanced. However, there are services for which that is not possible. For example, storage services or services that are stateful in a way that requires requests coming from a certain user to stick to certain tasks. In this case, when tasks get overloaded, they could offload some of the state to other tasks to keep the utilization balanced, but offloading the data itself may cause additional load, so the implementation is not trivial. Even at peak, it would be a bad idea to run tasks at 100%. As discussed before, some software, languages, or platforms misbehave or thrash at CPU utilization thresholds lower than 100%. Memory-wise, exactly hitting 100% means the tasks run out of memory and crash. It is also hard to actually measure what is the resource usage peak of tasks for the same reason as discussed before. Monitoring can't be fine-grained enough to capture the precise resource utilization in time windows short enough. Depending on the resource class, service, language, and/or platform, it is a good idea to aim for a maximum utilization lower than 100%. In this example, let's say the service misbehaves when hitting 80% utilization as measured by monitoring during load tests, so let's decrease the target utilization to 80%. Services need to have enough resources for them to be redundant at multiple levels and run reliably. The cost of running the service increases as it is made more redundant. Therefore, there is a trade-off between efficiency and reliability. A service can be redundant at task level. Tasks can crash or restart because of bugs, rollouts, hardware issues, or planned maintenance taking place in the computers they are running on. It is required to run multiple instances of a task in a region to guarantee that the service can serve requests from that region even if some tasks fail at once. When tasks fail, the capacity of the service in that region decreases, and the tasks that remain up and running need to be sufficient to put up with the load. If they can't, they will crash too, and a cascading failure will happen where all capacity is lost and human intervention is likely required to get the service back to a working state. A service can also be redundant at region level. A whole region or several of them can go down because of a combination of planned maintenance, a power outage, a network outage, or any other mishap. The service must have replicas in several regions, and it must be provisioned so that when one or more regions are down, the remaining ones are able to serve all the load. A service is said to be n+0 globally when it is up and running but cannot stand a region going down. It is said to be n+1 globally when it can stand a single region going down. It is said to be n+2 globally when it can stand two regions going down, and so on. Provisioning for n+2 has nice implications on reliability. Plant maintenance can happen in a region, which brings the service to n+1, and still the service can stand an unplanned incident in another region, which would bring it to n+0 but not cause an outage. At that point, the priority would be to mitigate or resolve the unplanned incident as fast as possible, or to finish or revert the planned maintenance work to bring the service back to n+1 as soon as possible. Otherwise, any other region suffering an incident would cause a user-facing outage. Note that if the regions are located in different countries or continents and traffic is routed to optimize for the lowest latency, failover will increase latency. On the cost of redundancy, the more regions a service is operating in, the lower the cost of running n+2 is. In this example, we have a service that takes 100 requests per second at peak. With only 3 regions, a service that is provisioned for n+2 globally needs every replica to be able to stand all the load in case 2 replicas become unavailable. Given each replica needs to stand 100% of the load and there are 3 replicas, the total provisioned capacity is 300% of the capacity needed to serve peak traffic. For a metric on efficiency, the maximum CPU utilization at level flight is approximated as the total incoming load divided by the load the service is provisioned to serve when all replicas are up. This is just an approximation because resource utilization may grow non-linearly compared to requests. In this case, the maximum CPU utilization is 100 divided by 300, that is 33%. That means when all replicas are healthy, they should never go above 33% CPU utilization for the service to be running at n+2. That is a quite low and inefficient utilization. With 5 regions, though, a service that is provisioned for n+2 globally needs every replica to be able to stand 1/3 of the global load, because if 2 replicas fail, there would be at least 3 of them still up. Given each replica needs to stand 34% of the load and there are 5 replicas, the total provisioned capacity is 170% of the capacity needed to serve peak traffic. Adding 2 more replicas almost halved the cost for n+2 redundancy from 300% to 170%. The maximum CPU utilization for this setup is 100 divided by 170, that is 59%. When all replicas are healthy, they should never go above approximately 59% CPU utilization for the service to be running at n+2. Compare this with only 33% of target utilization in the 3 replica setup. So, a service with more replicas can run at higher utilization without losing on redundancy. The more similar regions are, the better. If regions have different capacities, the service needs to be provisioned so that it stands the largest regions going down. That means each of the smaller regions needs more slack, and the overall capacity overhead for redundancy is higher. Heterogeneous replica sizes also make provisioning harder, as the capacities needed to stand the other 1 or 2 largest regions being unavailable would be different in each region. Stateless services, such as front-end services that handle user requests, receive traffic that can be distributed among replicas. Requests that read from storage services can also be distributed across replicas in different regions. Provisioning them for redundancy is trivial and follows the reasoning and math from this example. On the other hand, requests that are replicated across regions, such as writes, act differently. A single write to a replicated entity needs to eventually happen in every single replica. When a replica goes down, replicated requests, such as writes, do not cause additional load to the replicas that remain up. Of course, that doesn't come for free. When the replica is back up, it will need to catch up with any writes that happened while it was down, and that increases load in the replica that is recovering. The data needed to get the replica to catch up is actually served from the replicas that remained running, so the recovery will also increase the load on them for a while, ideally capped to avoid hurting low latency traffic across a set of replicas. Each service and actually each job in the service stack can receive a different proportion of replicated and distributed traffic, which need to be factored in the resource provisioning for the stack. In our example of target utilization, let's say redundancy decreases it to 50%. There are latency-insensitive processes such as batch processes, some asynchronous requests, maintenance work, experiments, or the helping other replica catch-up process after an outage. These processes add load on top of the latency-sensitive load that the service is dealing with. This chart shows a fictional batch process running daily between 1 AM and 4 PM and increasing the load by 50k latency-insensitive requests per second. The service needs to be provisioned for a higher peak, so the cost to run the service increases. Alternatively, priorities can be implemented so that latency-insensitive requests aren't served when the service load is peaking. Latency-insensitive load can also be rescheduled around to decrease the peak to provision for. In this chart, the batch process runs at a higher rate and fits in the non-peak time between 1 AM and 5 AM, hence it doesn't alter the peak. Any of these approaches must be deployed carefully. The service must have enough capacity to fit in all the latency-insensitive processes. Otherwise, these processes would pile up and fall behind. Additionally, scheduling of these processes can be hard to configure and maintain. If there are dozens or hundreds of jobs that run at hard-coded times and at estimated peak rates, it is difficult to reason about why those jobs run at those times. It may be okay to run latency-insensitive processes less often, but the service needs some of them to run efficiently. That is the case of, for example, compactions in a storage service that aggregate changes that were stored separately as incrementals. Falling behind on running these processes will make the service perform worse. This, in turn, makes the service more overloaded and less able to catch up on maintenance work. The service would eventually spiral out of control into an outage. So why not make the maintenance work run more often at non-peak in order to use any spare capacity to make the service more efficient at peak? That would in theory allow for a more tight and efficient provisioning. Exercise caution as well, as this strategy can trigger exactly the same issue. If at some point there is not enough capacity to run this much extra maintenance work at non-peak, the service won't run as optimally as it used to run, and it won't have enough capacity to run at peak. In our target utilization example, let's say latency insensitive processes decreased the target utilization to 40%. The last factor to consider is the unknown factor. There are many good reasons to throw in an additional padding of resources when provisioning a service. Spare capacity will keep the service performing as expected, latency and error-wise, when anything goes wrong. An unexpected performance regression accidentally makes its way to production, the service hits a new or hidden bottleneck caused by new features taking more resources than needed, performance decreased due to an ongoing outage, failover happens when a replica is down, or recovery happens when it comes back, caches need to warm up, backends suffered increased latency, resource usage unexpectedly shuffles around between jobs due to some change, or an interaction with other services or issues in production triggers an unexpected failure mode. Even if the service is performing properly, the resource forecast can be off. The service could become an unexpected success anytime after the launch of a new feature or after an event. Spare capacity will keep the service up right when it is getting the most traffic and user attention. Paddings in memory are especially important because tasks crash when they run out of memory. A burst of requests, a large request, or a combination of both can sharply increase memory usage for a short time. Memory leaks increase the memory utilization over time and make tasks more brittle and prone to running out of memory. Cache failures are also a source of increased resource usage. Caches can be latency caches, capacity caches, or both at the same time. Latency caches make the service run faster. Capacity caches decrease resource usage. When capacity caches malfunction, the service may not have enough resources to serve the load and will suffer an outage. So often, capacity caches are critical dependencies of the service. Interestingly, latency caches tend to turn into capacity caches as load goes up, and caches hide the fact that the service cannot live without them. A cache rollout that went too fast, a cache failure, or caches warming up in a region after an outage can cause the resource usage to skyrocket, to the point that the service may not be able to recover without human intervention. It is critical to ensure that a service can cold start in the event of an outage or of a failure in a capacity or latency cache. If at all possible, capacity caches are to be avoided. With regards to paddings for the unknown, there is again a trade-off between efficiency and reliability, given that the cost of running the service increases as more paddings are added for reliability. In our example of target utilization, let's decrease it further to 34% to leave some paddings for the unknown. As a summary on target utilization, a service cannot run at 100% at peak. It needs to run lower because it could misbehave at high utilization, then even lower for N+1 or N+2 redundancy, then even lower to fit latency-insensitive processes, then even lower to leave some paddings for the unknown. The numbers in the slide are fictional, but the target utilization can be as low as 33%, only taking into account N+2 redundancy if a service runs in only 3 replicas. The following are good practices to improve utilization and therefore the efficiency of a service. Paddings should be evaluated holistically in order to avoid stacking paddings over paddings. It is possible to prepare the service so that outages have a low impact when it runs out of padding. Some prevention mechanisms that apply are graceful degradation, which makes the service disable some non-critical features to relieve resource usage when it is overwhelmed, denial of service attack protection in case the bump on traffic comes from an ill-intentioned party, or load shedding, which consists of tasks rejecting requests fast when they are overwhelmed, so a routing layer above can retry them or eventually make them fail fast, instead of having the service waste effort on requests that are going to time out anyway. The service redundancy setup must be efficient. As discussed before, the location and amount of replicas of a service can greatly decrease the cost of running it. The service software should be optimized to use fewer resources, have no memory leaks, and be less prone to thrashing. Provisioning resources for a service properly requires an understanding on how many resources are needed to serve a certain load. Load testing consists of subjecting a certain stack or replica of the service to a heavy load to analyze how the service behaves at target utilization and above target utilization. Why is load testing needed? It is a bad idea to do provisioning based on an estimation of resources per load unit. For example, how many CPUs are used per request served. That would imply that a task that uses 2 CPU cores to serve 1 million requests per second needs double the processing power to serve double the requests, that is, 4 CPU cores per second to serve 2 million requests per second. That assumption is wrong. Resource usage doesn't scale up linearly because the software and operating system have an overhead on managing the state that could be non-linear. Or because the software could hit some other bottleneck on a different resource or limitations that are unknown so far, like RAM usage that could make the task crash. Load testing does not provide understanding on how many resources are required for a task to serve a load unit, but actually validates that a task with a certain amount of resources is enough to serve a concrete load. The service can then scale up to serve more load by increasing the number of tasks with a shape that has been load tested, and by increasing the allocation of other resources such as storage or network. Load testing can also run the service above target utilization to exercise the service failure modes in a controlled manner, that is, to see how the service copes with overload. Load testing makes the service reliable. Without it, there may be hidden bottlenecks, unexpected interactions when launching new features, unexpected interactions during catch-up after a region went unavailable and then recovered, caches could be insufficient to keep the service running efficiently under heavier load, and many other otherwise unknown scenarios that can trigger outages. Without load testing, failure modes are unknown and only exercised during an actual outage. Load testing also makes the service efficient. It enables engineers to deploy optimizations in production. To put it the other way around, every optimization should go through load testing to guarantee that it is indeed an optimization and it is safe to deploy in production. The metrics to monitor when doing load testing are error rate, high percentile latency, and resource usage. Continuous load testing in a small stack that is running at target capacity can alert on regressions during rollouts. With proper plumbing, it can even stop the rollouts before they hit production whenever the new version of the service is performing worse than expected or misbehaving. Why is load testing hard? Well, as discussed before, the target utilization is lower than 100% and includes some buffer for N+1 or N+2 redundancy. Load testing should exercise the target redundancy requirements so as to guarantee that the service functions properly when regions are down. However, it cannot be done in production by bringing down entire regions to make the service N+0. That is not load testing, it's a production outage that is potentially user-facing if the load testing stack starts serving errors. There are alternatives to bringing down replicas that still increase the load in the load testing stack. A routing layer can force enough load in the load testing stack for it to run at target utilization. The same routing layer can then fall back to the other replicas if the load testing stack is serving errors. That approach temporarily invalidates the load testing, but avoids an outage that impacts customers. Load testing in a non-production environment requires the synthesis of production-like traffic, which is always difficult and sometimes not even possible. For example, when trying to load test new features whose traffic pattern is still unknown. The maintenance work involved in this approach is also significant, as the load testing environment needs to be up to date with new features and the ever-changing traffic patterns. A good approach to evaluate new features before they are launched is dark launches. When doing a dark launch, the backends do all the effort to manage the requests associated with the new feature, but the results aren't sent back to the frontend and aren't shown in the user interface. The user will not notice that there's a new feature, but the service behaves as if the new feature was there. Not only the traffic has to be production-like, the environment has to be similar to the production environment. For example, if the load testing stack runs in a region that has 10 times the network bandwidth and CPUs that are 2 generations younger than in production, the stack will not behave as the production stack. The middle ground is load testing in small stacks, such as canary stacks. Canary stacks still run on production traffic, but if anything goes wrong, the outage will affect a smaller set of users. Stateful services, such as storage services or transaction processing systems, are much harder to load test. They require moving data in and out the load testing stack to keep hitting but not surpassing the target utilization. The data transfer itself, if continuous, causes additional load on the service and invalidate the load tests. Automation could prepare the load testing stack daily to hit the peak once a day, although the guess on how much data to move in or out can be off and make utilization fall short or soar above the target utilization. Definitely not easy. Another big barrier for many organizations is cost. In order to load test a service, it is necessary to have the spare resources to do so at scale, which obviously isn't free. Once services are provisioned for, the next step is to forecast resource demand and plan for supply. That process is called capacity planning. Why is capacity planning needed? Well, it makes the service reliable and efficient in the long term. In terms of reliability, running out of resources in a hypothetical future will cause an outage that is maybe not easy to fix at that point if it is not possible to secure more resources immediately. In terms of efficiency, more insights on long-term demand allows making strategic decisions based on how advances in performance in the industry go, trade-offs, and product decisions such as which features it is worth or viable to launch. Why is capacity planning hard? It is hard to estimate how many resources new services or new features will need. Sometimes, the demand depends on the success or adoption rate of a new product, and it will only be known after launch. In this example, the forecast was quite off. Forecasts can be, of course, updated over time, but the sudden increase in demand that was unplanned for could cause an outage if the resources needed to withstand the increase weren't immediately available. Sometimes, events such as the start or end of holidays or completely unexpected events drastically alter the traffic patterns. If the service is relatively new or has changed significantly from one year to another, it is hard to foresee the effect of these events in the traffic patterns, like in this example. Peaks in demand that aren't accounted for put the service at risk because there may be no resources immediately available to provision for them. There should be contingency plans ready for situations like this, for example, graceful degradation and load shedding. Changes in the distribution of users that are in different time zones alter the daily traffic patterns and can result in traffic becoming less spread out across the day, causing higher peak usage. This would render the forecasts invalid in a matter of weeks or months, like in this example. Then, capacity planning is not about forecasting a single resource class like in the previous slides. The number of dimensions is large and they can change in ways that are independent. As discussed a few slides ago, a service can use several resource classes. That is in the order of 1 to 20 values that need to be defined to plan capacity for the service. Let's factor in some sort of resource priority by replicating this table, let's say 3 times. For the sake of simplicity, let's say high priority, medium priority, or low priority. Depending on the service and the resource class, these could be for latency-sensitive load, batch processes, and so on. Resource priorities multiply the number of values that need to be defined by, let's say, 2 to 5, depending on the number of available priorities. A service can live in several regions. Let's factor them in by replicating this table, let's say 3 times, 1 per region. Regions could multiply the number of values that need to be defined to do capacity planning by single digits, tens, or hundreds, depending on the service. A service can consist of several subservices, the capacity for each of which needs to be planned for separately. Let's factor that in by replicating this table, let's say 3 times, 1 per subservice. That would multiply, again, the number of values that need to be defined. Finally, capacity planning is about forecasting the supply and demand. Let's factor time in by replicating this table, let's say 4 times, 1 per quarter, that is for 1 year. Depending on the granularity, which could be, for example, monthly, quarterly, or yearly, time would multiply the number of values that need to be defined to do capacity planning by a couple to tens per year. Summing up, depending on the infrastructure, the organization, and time granularity, the complexity of capacity planning can range from defining tens of values to thousands of values per year. Pooling is a strategy that can be applied to decrease complexity on planning and also resource fragmentation, hence improving the efficiency of the services. Pooling consists of grouping resources together so that several services can share them instead of having separate allocations of resources per service. When doing pooling, large services can be planned for with detail and precision, but small services can use a pool of resources that is planned for as a single entity, approximately and conservatively so as to decrease the effort on capacity planning. The main disadvantage of pooling, though, is that it doesn't necessarily offer isolation between services. A service that is misbehaving and using more resources than it should could impact other services. To finish this presentation, I am presenting some good practices on capacity management solutions that apply to all of provisioning, load testing, and capacity planning. Monitoring the relevant metrics provides data to guide resource provisioning and capacity planning decisions. Load metrics are useful metrics. Examples are incoming requests per second, batch or asynchronous load, or number of users. Resource allocations and actual usage are also useful metrics. Performance metrics such as latency and errors are useful as well. Finally, high-level health metrics such as when the service was impacted by an outage can help filter out other metrics data that would not be useful to guide resource provisioning and capacity planning because it was tainted. Alerts on resource provisioning and capacity planning prevent outages. Some examples of useful alerts are those that trigger when the service is not running at N+1 or N+2 anymore and is therefore under-provisioned, or alerts when the service would lack resources in the future according to forecasts. Additionally, and critically, teams should carefully review any outage caused by avoidable shortfalls in capacity. These should be put through a blameless postmortem process to determine whether they suggest changes to capacity planning, provisioning, load testing, or alerting processes. Changes to production must be reviewed by someone other than the proposer. Especially when dealing with capacity, an incorrect change can trigger a global outage in a service. Production state, including the resource allocation per task, the number of tasks per job, the number of replicas and what regions they are located in, must be configuration-based and version-controlled. The opposite would be a stateful ad hoc production setup which engineers modify without documentation or tracking on the changes. For example, by running command line interface tools or SSHing into machines and changing configurations. Such stateful production setups are bad because intention is not explicit. So it is hard to tell in what state production actually is. Furthermore, any tools or dashboards to query or aggregate the actual state can hide details when they are stale. A configuration captures the intention clearly. Graphical interfaces that modify the production state, such as web interfaces, are bad. They are prone to accidental changes, for example by someone accidentally clicking on some random button in the interface. They may also not support a review mechanism, and they may not even store a history of the changes. Command line interface tools that modify the production state are bad because it is hard to enforce reviews on the proposed changes when using them, and they are prone to accidental changes too, especially when copy-pasting and editing commands. Changes to configuration files checked into a source control system are easier to review. Everything capacity management related, from provisioning to capacity planning, including load testing, should be automated and run without human intervention. Automated enforcement or actuation of the desired production state avoids the piling up of differences between intention and production state. This is not just good from a capacity management point of view, but it is good for reliability in general. Spurious differences in state between configuration and actual state in production can otherwise delay action when trying to mitigate an outage. For example, when an engineer is trying to do a production change to mitigate an outage and an unexpected difference in state shows up, the engineer has to debug it, understand it, and revert it, which takes time. A pile-up of differences in state can be so hard to revert, and an outage can be so bad that the hard decision is made to push the pile-up of changes to production just to be able to push the change to mitigate the outage. Pushing unknown changes to production can introduce interactions or break the services in ways that can exacerbate the impact of the outage or cause a new outage. In the ideal case, the state of production follows intent that is described in configuration files that are checked into the source control system. Automation will then take care to update the jobs to follow the intent in the configuration files, of course obeying rules for gradual rollouts and such. Rollouts have to be gradual. A change that rolls out all at once in production will trigger a global outage if it goes south. A good practice is to first roll out to a small fraction of the capacity, for example 0.1%. Then monitor to see that these 0.1% of tasks are performing as expected. Only when that is the case, roll out to 1% of the capacity, again monitoring for misbehavior. Repeat with 10% and finally 100%. Each of these steps could take hours or even a day for soak time. As a closing note, avoid aiming for the perfect capacity management solution. There is so much to learn on the way and so many changes on flight. Aim for the lowest hanging fruit, deploy the minimum viable product, and then iterate. Let's wrap up. I have talked about resource classes and the particularities of some of the most common ones. Resource provisioning to ensure that a service can run, load testing to guarantee that the provisioning is accurate, capacity planning to forecast demand in the long term and adjust supply accordingly, and some good practices on the implementation of capacity management solutions. That's all for this Tech Talk. I hope you enjoyed. Thank you for watching. Cheers!